Anyone? Okay, so standard deviation essentially indicates the spread about your mean, or tells us about the spread about your mean. Oh, that's weird. All right, so basically what that means is it tells us how spread out our data points on either side of our mean value is. It's just a measure of spread. It tells us how clustered together the points are, how spread apart they are, but specifically relating to the mean. Right, and then oftentimes once we've got our standard deviation, we're going to get a question like 1.1.2 that says how many players are within one standard deviation of the mean. Often it's 1 or 2 standard deviations. There is a statistical reason for this. It's just that anything greater than 2 standard deviations is generally not a good indication of your data. That's where we start getting outliers. Oops. So generally statisticians, don't know why that word was hard for me to say there, but statisticians work within, in terms of what is reliable data, 1 standard deviation, sometimes 2 standard deviations of your mean. Okay, so how many players are within 1 standard deviation of our mean? Essentially what we're wanting to do here is we're wanting to take our mean and subtract the standard deviation, and then take our mean and add a standard deviation. Don't know why I went theta there. Let's fix that. And that will give us all the players within 1 standard deviation. So that's exactly what I'm going to do. If I take my average and I add 4,14, so let's not do that. Yeah, actually, sorry. My brain. So if I take my average, let's first subtract, and I subtract 4,14, I get a value of 21,86. And if I take my average or my mean and add the standard deviation, so 26 plus 4,14, I get 30,14. So essentially what it's saying is that when I go back up to my data set, I want the data points that have values between 21,86 and 30,14. Those are the values within 1 standard deviation. So 29 definitely falls within that range. So does 27. So does 24. 31 is too big. It falls outside my range. 22 is in that range. 19, too small, doesn't fall within my range. 30 is fine. So there are 2 data points out of the 7 that fall outside of 1 standard deviation, which means that within 1 standard deviation, sorry, I have got 5 data points. Okay, so just be very, very careful to read your question carefully. It says how many, so there are 5 players. It said how many players? 5 players within 1 standard deviation. Right, so sometimes it says how many players are or fall outside of 1 standard deviation, and then it would be the 2 that we just identified. But read your question carefully in order to figure out what it is they're asking. Sometimes we say what percentage of data points fall outside of 1 standard deviation. It just depends what your markers or your exam setter is feeling. So just read your question really carefully. And that's what I was saying earlier before we started. Stats is about interpreting and understanding your questions. Okay. Let's do 1.1.3, and then I will make it a bit smaller for us to screenshot. So 113 says 7 players of the school's rugby team also recorded the number of push-ups they completed in a minute. Their numbers gave a mean of 26 and a standard deviation of 3.2. Use the standard deviations and the means to compare the number of push-ups of the players in the rugby and the hockey teams. Okay, so obviously we have all of this information. You don't need to rewrite it. It's not necessary. But we have rugby. We have hockey. The only reason I'm doing this is so we can start to compare. We have mean, and we have the standard deviation. Right, so rugby, they've just given us that the average is 26 and the standard deviation 3,2. Hockey, the average we also worked out to be 26, but the standard deviation 4,14. So when we start to compare, we just need to be careful because my averages are exactly the same. It's a standard deviation that's different, and that's going to tell me something about the number of push-ups each team is capable of doing. So the mean is the same, but our standard deviation, that's a weird, whatever that is. Our standard deviation of the rugby players is lower. I have yet to actually answer the questions. I've yet to actually compare. I've said what's happening, but I haven't actually made a comparison. So now we have to say what this means. So this lower standard deviation means that that the rugby team, maybe I should speak first and I'm all right. The rugby team has data points more clustered around the mean, and so they have a more similar number of push-ups that the players are able to do in comparison to the hockey players. We saw that we had 2 points, the 31 and the 19, that fell outside of one standard deviation. And so that might not be the case with the rugby players, but it means that our rugby players' data is more clustered about the mean. And that's exactly what I said standard deviation means earlier. Right, and just so that we understand, when I talk about data points being clustered around the mean, I'm saying there's more data points closer to the average for the rugby players than for the hockey players, right? So what that means is that the rugby players' number of push-ups is closer to, more similar to the average than the hockey players. Okay, so we need to just make that comparison. So yes, we've said the mean is the same and standard deviation of the rugby players is lower, but we actually need to go ahead and say what that actually means. All right, so like I say, first question is generally a very stock standard grade 11 level question, standard deviation, mean, and then some sort of interpretation with that information. And like I say, oftentimes you are asked within one standard deviation, within two, one standard deviation above, below, whatever. Just read your question carefully to make sure you are working out what they've asked you to work out. Right, then one of the visual representations within statistics that you need to be comfortable with is a box and whisker. So if we have a look at 1.2, we have a box and whisker here that is representing the number of points scored by a rugby team in 10 matches, which is shown below. And then it tells us that the scores of the 10 matches were different. So basically, no match produced the same score. Makes sense. Rugby, generally, your scores are not the same. So no score was the same. Basically, what that means is there's no modal score. There's no modal value. So 1.2.1 says what percentage of the matches, in what percentage of the matches did the team score over 30%? 30%, 30 points. Okay, so this is now where understanding what a box and whisker actually says to us is quite useful. All right, okay, doesn't matter that I'm showing my full screen, doesn't matter. A box and whisker is based on your 5-number summary. Okay, I'm just going to be lazy there. It is your minimum, Q1, Q2, or your median. Sorry, my cat's head is in the way. Q3, and then your maximum. Those are the 5 numbers that we use when we go and draw a box and whisker. So that means that this value over here represents my minimum, Q1, Q2 or my median, Q3, and my maximum. Right, now what we need to remember is that Q1, Q2, Q3 are our quartiles. Quartiles represent, as the name suggests, quarters or a split. into 4 parts. Now, importantly, there are 4 equal parts. So what that means is from your minimum to Q1, we've got 25% of our data points. From Q1 to our median, we have 25% of our data points. From Q2 to Q3, another 25%, and from Q3 to our maximum, 25%. The sizes of those sections are different depending on how clustered or spread out my data points are. So let's say, for example, okay, just because I'm lazy and I don't want to have to work out points here. Let's say, for example, we had 8 data points, which means each quarter would have 2 data points. So 2 data points, 2, 2, 2. In this sort of section over here, these 2 data points would be very different, very spread out from each other. Whereas here, because it's a much smaller little section, the data points would be much closer together. So they all represent the same percentage of your data. It's just their size in terms of the box and whisker segment is indicative of the spread. So now that we've spoken about all of that, it says, in what percentage of the matches did the team score over 30 points? So here's my 30 points. And everything above that is over 30 points. Now, 30 represents my median. And I can see that there because I've labeled it. And so if we go and have a look at our percentages that I've just labeled, below your median, you've got 50% of your data. And above your median, you've got 50% of your data because your median is your middle point, 50-50. And so what that means is that in 50% of our data, the team scored over 30 points. Right, that's a 1 marker. There's a reason for it. You literally just have to read. My boy. Let's do this over here. Okay. So it's not a hard question, but obviously if you don't understand what the box and whisker represents in terms of the spread of your data and the grouping of your data, it is a tricky question. 1.2.2 then says, which of the mean or median is likely to be greater? Give a reason for your answer. Okay, now when we talk about stuff like this, this is relating directly to your skewedness of your data. I'm not sure if that's actually a word, but it is now. Right, now we did speak about this in our actual lessons on stats, but I'm just going to recap it again because it's not hard, okay? It's not hard to understand what skewedness is. It's not hard to say that your data set is positively or negatively skewed. It's not hard to talk about where your median is greater than or less than or whatever. But again, if you don't know, then you're not going to be able to do it. So we're just going to go on the side here. Okay, my drawings are not going to be great, but it's going to be fine. Right, so you get different types of spread in your data set. So if we look at this beautiful box and whisker that I've just drawn here, we can see that this box and whisker is perfectly symmetrical or very close to symmetrical. When your data set is symmetrical, essentially what that's saying is that each quartile contains an even spread of the same number of points, data points. And so what this indicates to us is that our mean is equal to our median. There is no outlier or there's no smaller or bigger value pulling one bigger than the other. It's symmetrical. Our mean is equal to our median. We then have skewed data. Okay. So we have data that is positively and negatively skewed. Just bear with me in my beautiful diagrams. And I am exaggerating this. Okay, so please understand that this is exaggerated. It's so that we can see what's happening. All right, so we're going to get there eventually. If we just go back to what our data represents, remember, obviously 25% all the way, but if we just look at 50%, symmetrical, 50-50, pretty even Stevens. When we now get to this next box and whisker, this small little section from minimum to median represents 50%, but this whole long situation over here also represents 50%. My data is much more spread out in the top half. There's something pulling it up. And when it's pulling it up, this is where we have a positive skew or skew to the right. Right now, if we think about what that means, is there must be a value that is much bigger than the rest of my data points, pulling the data set up, so pulling my box and whisker to the positive side or to the bigger values. And so what that means is that if you think of it in terms of that there's an outlier or a much bigger value pulling it up, we know that that much bigger value would pull my average up. If everyone in the class is getting 50%, but someone gets 90, that's going to pull the class average up. So this is now where our mean would be greater than our median. Right, and then finally we get negative skew. Again, I'm exaggerating the diagram, so please just bear that in mind. Again, if you look at your split 50-50, all of this here is 50%. Yeah, 50%. So it's the same number of data points, just how spread out they are. And because there's clearly a value pulling my whole spread down, so again, think of it in terms of a median, this is a negative skew or skewed to the left. It's pulling down to the left. Sorry guys, I'm sick, and clearly some consonants and vowels are being missed in my speech. To the left, and again, if you think of it in terms of your mean, what that means is that your mean is being pulled down, so it'll be less than your median. Right, now knowing all of that information is going to help us answer this question. If we did not know any of this information, answering this question is going to be a whole lot harder. So if we look at our data set, here is 50%, as we've already indicated, here's 50%. We have a situation where the data set is more pulled up to the right. So we have this situation over here. So what that means is that it is likely that my mean is greater than my median. It says give a reason for your answer. Well, our reason is because our data is skewed to the right, or our data is positively skewed. Okay, so understanding your box and whiskers, very, very important. Now, again, grade 12s, these two questions is worth 3 marks. Okay, it doesn't seem like a lot. And realistically, like, it's not that much. But if you think about it in terms of what it represents for you, in terms of your test, that's 2%. Your test, your exam, it's 2%. So just by understanding what a box and whisker is and what information it gives you, you've guaranteed yourself 2% in your exam, which again doesn't sound like a lot, but it's the difference between a pass and a fail. It's the difference between your A and your B. It is a difference between a 40 and a 50. It is a big difference that you are easily able to guarantee for yourself. Okay, so I'm going to stop here, take your screenshots. Obviously, guys, you know that if you have questions, you just ask. Okay, I'm going to assume that if you have questions, you're going to say so. You guys are pretty good with that, so I'm just reminding you. I don't think I need to. I'm just letting you know in case. All right, so that's the grade 11 level question, and then we get to grade 12, which is the regression line of best fit, or least squares regression line, etc., etc. So just so that we're aware, grade 11 data also, grade 11 statistics or data handling includes ogives. So in this case, we didn't ask an ogive. It just depends on ogive, however you say it. I say ogive. It just depends again on the examiner. I'm gonna say most of the time we tend towards an ogive, but obviously every now and then it's a box and whisker. Sometimes like a frequency polygon or like a histogram or something, but it's usually a box and whisker or an ogive. And like I say, 70-80% of the time we tend towards ogive, but obviously we can ask you box and whiskers. It's part of your syllabus, so just be mindful of that. Alrighty, let's have a look at the next one. So this is now where the grade 12 stats regression comes into play. Okay, so we've got a table shows the percentages scored by a sample of 15 candidates in the third term and the final examinations of 2022. The table and the scatter plot below represent these marks. So we can see that third term on the x-axis, final on the y-axis, we've got a scatter plot. And what we just need to remember is that the trend shown by a scatter plot relates directly to the correlation. Okay, now we're going to talk about all of this in a second. But I do just want to say something because it came up now in the mock paper in the Western Cape. And it's not actually something I ever knew we were so strict about, but apparently we are. And so I just want to make a point of it. Like I say, it's like even veteran teachers were a little bit shocked in terms of the marking, but I just want you to be aware of this so that you know. These questions don't ask this at any point, so we're not gonna actually need to do this. But if you were asked to draw your least squares regression line, okay, obviously we can find the equation of it. Lovely, lovely, lovely. If you are not sure how to draw it, all you need to bear in mind is that when you draw your line, you want the same number of points above as below. So obviously you're never going to get it perfect. It might be like 4-3 or like 5-3, but you kind of want an even spread above and below your line. Okay. So this is where I was a little perturbed, but this is how we mark, so just be mindful. When you draw this least squares regression line, we do not extend from one end of the Cartesian plane to the other. And I'll explain why that is in a second. So when you draw the least squares regression line, you can go a little bit below and a little bit above, but basically you need to go within the domain of your data set. Okay, so that would be a fairly decent least squares regression line. Now, the reason for that, and it does make sense, I just did not know that we were this strict in marking it until these prelims came about. So I'm just letting you know so that should it come about in finals, you're aware of it. And obviously, I'll talk about it again when we do finals prep. So the reason for this is, obviously, we know about extrapolation and interpolation. So extrapolation is if we go outside the domain of this data, we can start to make predictions, but obviously those predictions become less reliable the further away we get from our data set. So what I mean by that is, if we were to go and try and predict the mark of someone who got 5% for their third term exam or their trial exam, it's not going to be a very reliable prediction because it is so far away from the rest of your data set. A least squares regression line describes the trend for the specific data points we have. It doesn't go further than that. We can start to make predictions, absolutely, but the further away we get, the less reliable it becomes. And this is why we don't actually extend our line. The line, if extended, would say that any point along this line follows the trend, okay? And it doesn't necessarily, and we learn that when we talk about regression. So this is just a very random little tidbit of information in terms of marking. Don't extend your line all the way. A little bit beyond is absolutely fine, but stick within the domain that has been given to you. Okay. I don't think it usually happens, but I know that for us in these exams, we had to take off a mark if the line was extended all the way. So it's a very silly thing to lose a mark on. And if you don't know about it, again, you probably would extend the line. I personally would have extended the line before this. But it does make sense why we shouldn't. So just bear that in mind. Okay. So anyways, we've got all of our data. And obviously the first question is asking us to determine the equation of the least squares regression line for the data rounding off to 3 decimal places. Excuse me. Okay, so again, we need our little calculator friend. There he is. Sorry, I turned it off. We're again in stats. However, now when we choose our options, we're not going to go into the mean and standard deviation and all of that. We want to select option 2, which is A plus BX. Now, This allows for bivariate data. So that's why there's an X and a Y. Bivariate, bi, two, variate, variables. There's two variables. There's the third or the third term exams, the trial exams, and the final exams. We've got two sets of data. So we need to fill all of this in. It is slightly tedious, but it is what it is. Here we are. So I'm filling in all of my third term marks. It would be so nice if I could just type this with my fingers. But anyways, oops. This is probably the most time-consuming part of stats. Everything else is quick. Once it's in your calculator, you can pretty much do anything you need to do. Pretty sure they told us it was 15 candidates, so it obviously wasn't because, oh no, it was. So here I am at 15. Just make sure, 15 candidates. I can double check, I've got 15 data points, that's great. I now move over to my Y values. Again, the most time-consuming part of stats is typing nonsense into your calculator, but once it's there, it's there. Right, there we go. Okay. Again, once you've done that, you can push AC. It makes no difference if you do or don't. Don't worry, your data is not lost. It's not gone. It's just stored. Right, so we want the equation of the least squares regression line. Now, remember, your equation for your least squares regression line, I will put the calculator back up now, obviously, is y is equal to a plus bx. It's exactly what it shows you on your calculator. That's why we choose this option on our calculator, because that's what we're wanting to find. Right, I will tell you how we need to, or what we need to bear in mind when we do this. However, we go shift 1 to stat, and now we're going to option 5, regression. We're talking about the least squares regression line. So we click 5. Oops, it would help if I picked an option. And I want A and B. Doesn't matter what you start with, so I'm going to start with A. So A is 9,035. Remember, it's set to 3 decimal places. Right, and then we go back and we get B. Okay, again, you just go shift 1, regression, option 2 for B, and we get 0,895. And so our equation of our least squares regression line, we put a little copy on the Y to show that it's the least squares regression line that we're talking about, and this equation is 9,035 plus 0,895x, and that's it. Now, just quickly in terms of this marking, you can just go straight to your equation. You don't actually need to write down A equals B equals and then put it in the equation. You can go straight to the equation. However, in terms of marking, if you put it into your equation wrong, then it's 0. Okay, so that's why I always like to just write down A and B. Just in case you flip those two values, you can get some marks. But obviously, if you're super confident with your equation, you can go straight there and you will get all 3 marks. Okay, so you will get 4 marks for your answer. But if you swap the values in, unfortunately, it's 0 if you've only written down the equation. At least if you write down A and B, you can get marks there. Okay, I'm going to make this ever so slightly smaller, just so that we can have a look at the scatter plot in relation or in conjunction with this next question. So 2.2 says, write down the value of the correlation coefficient R between the third term and the final exam percentages. Again, you do this on your calculator, right? There's no need to try and do anything by hand here. Shift 1, regression. And now we want R, the correlation coefficient. It's option 3. And it's 0,982. You can just leave it at 2 decimal places. There's no need for you to do more than that. Now, one of the next questions is going to ask us this, but so that we have an answer. Can anyone tell me what that actually means? What does a correlation coefficient of 0,982 mean? Okay. Okay, so Layla, perfect would be 1, but this is pretty close to perfect. Okay, so if you round it off to a whole number, absolutely. But I agree, we would say it's a strong positive linear correlation. Good, Bongi Nkosi. So perfect correlations, if it's positive, will be R equals 1. If it's negative, it will be equals -1. We did do a summary of all of this when we did our stats section. I've got a summary sheet somewhere. I'll put it up for you guys on Google Classroom. I'm not going to try and find it now because I'll never find it now that I want it. And basically, as you then move in from those limits of 1 and -1, you get strong, moderate, weak, no correlation. There is a summary, and I'll put it up on you. I'll put it on Google Classroom for you. But this is a strong, positive, linear correlation. You do get other types of correlations. It doesn't have to be linear. We just happen to only learn about linear correlations. So you need to give me whether it's positive or negative, strong, moderate, weak, no correlation, and the fact that it's linear. So there will be 3 adjectives describing your correlation. It didn't ask us for that there, so we don't really care about it at this point. But there is a question coming up where we are going to use that. Okay. So if we have a look at this next set of questions, actually, let's maybe take a screenshot before we just, rush. Let's take a screenshot of that, and then we'll look at the next little bit of questions. Okay. So 2.3 says a candidate scored 48% in the 3rd term. Use the equation of the least squares regression line to predict his final percentage. Round your answer off to the nearest whole number. Okay, so we've been told to use the least squares regression line. We'll chat about why it makes sense to do so now in a second. But our equation was y is equal to 9,035 plus 0,895 x. Okay, now remember, x and y are your variables. So if we go back up to our scatter plot, the 3rd term mark is x. The final mark is y. So we are substituting in for x because that was the 3rd term mark. So y is equal to 9,035 plus 0,895 x, which is at 48, and it's just a basic substitution and solve. Right, you get 51,995. If you read the instructions in the question, it says round your answer off to the nearest whole number. So this learner will get approximately 52% in their final mark. Right, now this is where correlation and what it means becomes important. The next question asks, give a reason why this prediction can be regarded as reliable. All right, so there's 2 sort of statements that you can make, and it's based on everything that I've already said. Option 1 is you can use your correlation coefficient. So that was 0,982. Right. As we've already said, this is a strong, positive, linear correlation. Anytime you have a strong correlation, positive or negative, any prediction that you make, particularly within the domain, is going to be reliable. As you start to extrapolate, so move outside of your domain, it's still reliable, but only to a point. Okay? If you keep going too far away from your data points, it's eventually going to become unreliable. So that's one reason that you could give. Reason number 2 is exactly what I just said now. This value of 48 falls within the domain of my data set. So if I go and have a look here, my 3rd term marks go from, what was the lowest that we had? 41. No. Yes, 41 to 90 something. the 48 is within the domain of that data set. So it falls along that line. It's not going too far away. We're not starting to sort of move away from reliability. So we could also say 48% is within the domain of our regression line. Now, I think most of you would probably give the first reason, and that's absolutely fine. You don't give both, you have one or the other. I'm just explaining to you why you could use the whole domain conversation as a reason for your answer that we had earlier. But again, most of you are probably going to go with option one in terms of the fact that we had a strong correlation coefficient. And so that means that my prediction is reliable, and that is perfectly sufficient. All right, let's just move some of this up because this seems like a real waste of space here. Okay. So 2.4 says no, it doesn't say that. It says the least squares regression line is used to predict that the final percentage of a candidate who scored 50% in the third term is 80. Okay, so now it's asking why would this prediction be unreliable? Well, let's go back up to our scatter plot. 50% in the third term, so there's 50, and 80% in the final. So this point is sitting somewhere over here. I hope we all agree that this would be considered an outlier. It's sitting way too far away from my regression line to follow the trend. Okay, remember your regression line indicates a trend of your data. That is nowhere near the trend. So that would essentially reason why it's unreliable. Okay, that data point of 50%, 80%, I'll put it right in 8. Obviously, you don't have to put the percentages there, you can, would be considered an outlier. Sure, can't spell. And so doesn't follow the trend of the regression line. I'm being very lazy in my writing. Okay, so when it asks you again something like this, look at your data set, look at what it means. Obviously, another option would just be to use your least squares regression line. And you could say y equals 9,035 plus 0,895 and substitute in your third term mark. And you would see, I think it gives you 84. Don't know where I was going with that. It doesn't give you 84, obviously, because that's nonsense. It gives you 54. And so you could see that a third term mark of 50 does not give you a final mark of 80. And so you could then also reason that if you use your least squares regression line with that prediction, it doesn't follow the trend. All right, but use your data set, understand what your data set is saying to you, and then you should be okay. Right, I'm just going to stop here for a screenshot, and then we'll have a look at the last question, because I need to go back up to our scatter plot to answer this last question. Right, so the last question says, would adding the point 2010 to the original data set increase or decrease the gradient of the least squares regression line? So let's see, we are adding the point 2010. So let's make this quite obvious. 2010 would be that point over there. It's a bit dramatic, but you get the general gist of the situation. Right, it's also not super clear, but hopefully we get that. So what it's saying is, if I now had to consider that point in my least squares regression line, what's going to happen? Now think about it. We now have to include this point somehow. my least squares regression line is going to start to look something like that. And what's happening, we can see, is that it starts to get steeper because we have to include that data point. And so when it asks, would adding the data point increase or decrease the gradient, we can clearly see that it's going to increase our gradient. Okay, so I'll leave it there in case you want to screenshot it with the visual. But again, use your data points, use your scatter plot, use your ogive, use your box and whisker, whatever the case is. Draw on it, scribble on it. You get these diagrams in your answer book. They're yours to do with what you want. Use them so you can figure out the answers to your questions. Excuse me. Okay, so hopefully what you can see is that none of this is actually too tricky. The only one that maybe was a little bit tricky thus far that we've done was this question over here in terms of the skewedness. I don't think anything else has been tricky. It's all a case of, do you know your work? All right, so let's have a look at this question over here where now we're being tested on ogives, which is, like I say, the more likely scenario, but not necessarily the only scenario. So we've been told that the cumulative frequency graph, or your ogive, is drawn below. It shows the total number of food items ordered from a menu over a period of 1 hour. Okay, before we get into the questions, we can't even see the questions yet. Let's just chat about what an ogive is, what it represents, what we're looking at when we look at one. Right, firstly, cumulative frequency graphs or ogives represent the cumulative, but it also represents grouped data. Okay, so when I say grouped data, these are intervals. This is 0 to 10, 10 to 20, 20 to 30, 30 to 40, etc., etc. So this is all grouped data. These are our intervals. Now, if you are asked to plot an ogive, which you're not often asked to plot one, but if you are, you always ground your ogive at the lower limit of your first interval. So what that means is that that first interval starts at 0 and goes up to 10. This point over here represents from, so this is from the first interval. This is now the end point of your first interval. And each of these subsequent points are the end points of your interval. Okay, so where the interval ends. And so what we need to bear in mind is that oftentimes what's going to happen is because we're going from 10 to 20, one of those values will be included or excluded. And because this is the end point, oftentimes we're going to go and include this point, exclude that. In the next interval, include, exclude, include, exclude, and so we keep going. All right, so just bear that in mind. A cumulative frequency graph talks about intervals, plotting endpoints of intervals, and obviously the frequency as it accumulates as we go along. Right, I just want to take all the scribbles off, otherwise it's going to get a bit confusing. Let's maybe do a little thing here. Plot, interval, endpoints. Okay, so that's just if you have to draw one, but oftentimes we give it to you and you then go from there. Right, so the first question is asking, write down the total number of food items ordered from the menu during this hour. Now remember, because it's cumulative frequency, it's accumulating. This final point over here, the y value represents n, so how many. So all we do is we read off the cumulative frequency, it's 140. So within this first hour, there were 140 food items ordered. That's it. Okay, nothing more, nothing less. 1.1.2 asks us to write down the modal class of our data set. Okay, now modal class has the highest frequency. And we can tell this on our ogive by looking for the biggest gap between points. Okay, again, I'm sorry, I'm being very lazy in my writing, but we get the gist. So when I say the biggest gap, basically the biggest distance between points. And we can see that the biggest distance between our points is between 20 and 30. That has the greatest gap. And so the interval 20 to 30 is my modal interval, my modal class. So 20 to 30, and remember, like I said, we generally include the first one, exclude the next one, and then for the next interval, we would include the 30, exclude the 40, next one, include the 40, etc., etc. Right, that's it. Modal class, biggest gap, look for that, write it down. 1.1.3 says, how long did it take to order the first 30 food items? Now, OJAB questions is very much your ability to read information off a graph. So the first 30 food items. So we go to 30 because that's the number of food items that we are working with here. And we are going to then read across to the time. So we read across, we hit our graph, we read down to the time. And it actually happens to be nice and easy to read off 20 minutes. Okay, so what you're going to see is that the next 3 questions is all your ability to read information and use your OJIVE graph. Right, 1.4 says, how many food items were ordered in the last 15 minutes? We love asking questions like this because we often 45 minutes. So it's an hour. We are going to go to 45. 1, 2, 3, 4, 5. So this line over here, this is 45 minutes. These are the last 15 minutes. So we're going to read up. Again, I'm going to do my absolute best to draw a line. Obviously fail miserably at that in any case. Nope. Cool. Okay, there we go. And once we hit our graph, we read across. Oh, no, it didn't. It wasn't good. Right, anyways. 21, 22, 23. 26, because it's going up in twos. 2, 4, 6. Okay, so that's 126. Now, what we need to remember is that this is cumulative frequency. So what we have just read off is the fact that after 45 minutes, I don't know why I put degrees there, so that's cool, that after 45 minutes, 126 items were sold. That's this point of information that we have just got. The question asks, however, how many food items were sold in the last 15 minutes? Now, if we know that 140 items were sold in total, and we know that after 45 minutes, 126 items were sold, we can go and work out the difference. So we would need to take the 140 and subtract the 126, and we would get that 14 meals were sold in the last 15 minutes. And this is a question that often stumps us because what we don't do, we go and perfectly read off that at 45 minutes, it was 126 meals. What we don't do is subtract. So read your questions carefully, make sure you are actually answering what you've been asked to answer. And just bear in mind, it's cumulative frequency. Okay, that's really important. Right, 1.1.5 says determine the 75th percentile of your data. Now, what this should be saying to you is that 75th percentile is Q3. 75% of your data is quartile 3. Now, that doesn't make a huge amount of difference, but it is going to help us in the next question. So first thing that we want to do, grade 12s, is we want to work out, if I know that I've sold 140 food items, what is 75% of that? So we want to work out 75% of our total. 75% of 140 is 105 food items. And because we now know how many food items indicate 75%, we go back up to our graph. So we want to go to 105, 2, 4, so it's about there. Okay, it's not going to be my best attempt in the world, but we're going to try. We draw a line. It wasn't good. I'm going to try once more, otherwise we're just going to move on from it. Okay, there we go. Hit our graph, and then we read down. Also, just bear in mind, grade 12s, there's always some degree of like leniency with these sorts of things. You are reading it off a graph. You're doing the best that you can. There is a degree of leniency. Okay, this is about 1, 2, 3, 4, 5, 6. This is about 37 minutes. Okay, so what this is saying to us is that the 75th percentile of our data is at 37 minutes. There's usually a range of 1 up, 1 down, so we would accept between 36 and 38. Just that you are aware of that. There is usually a range in which we accept your answers. Okay, and 1.1.6 now asks us for the interquartile range. So interquartile range, remember, is us taking Q3, which we've just found, and subtracting Q1. So we would still need to go and find Q1, but Q1 is 25% of my data. So we would now go work out what 25% of 140 is. That is 35 food items. And so again, we go up to our graph. We go to 35 items, which is about there. We read across. Okay, we read down. I'm going to do my best to get this as accurate as it should be. It's halfway between 21 and 22, so it's about 21.5 minutes. Again, there would be leeway. All right. So Q1 is at 21.5 minutes. And now we can work out the interquartile range. 37 minus 21.5 gives us 15.5 minutes. Essentially, what your interquartile range says to you is that the difference from the difference in the middle 50%, your range in your middle 50% is 15.5 minutes. So the spread of your middle 50%, there's a difference of 15.5 minutes from the lower limit of your first quartile to the upper limit of your third quartile. 15-minute spread. That is what an interquartile range does. Think of range. It's your maximum minus your minimum. Interquartile range is just not for the middle 50% of your data, but represents the same information. Okay, so let's take a screenshot of this, and then I'll put the questions up. Okay, and here are your questions. There we go. That's all of them. And guys, much like what I was doing, if it helps you to have colors and highlighters and whatever, when you are using your ODrive, do that. Okay, we've had this discussion already that we mark your diagrams. So even if, for example, let's say this question over here, 1.1.3, let's say, for example, you didn't write your answer down, but you've shown it on your graph, I can mark that. So use your graph, draw on it, sketch on it, do what you need to do so that you can actually get your marks. Okay. So 2.2. 1.2 says Reggie works part-time as a waiter at a local restaurant. The amount of money in rands he made in tips over a 15-day period is given below. And we are asking you to calculate the mean and the standard deviation of the data. So I'm going to give you 2 minutes, 3 minutes. No, maybe a little bit longer than that. 2 marks each, so 4 minutes. I'm going to give you 5 minutes to input your data and work out the mean and the standard deviation. You can put your answers in the chat, so you help each other to check. If you have questions, you ask, but I'm going to give you 5 minutes to go and work out those 2 pieces of information for me. Okay, I'm going to give you 1 more minute and then we'll have a look. Okay, so Layla has put it on the chat. However, our mean X bar was 94. Interesting. That was weird. 94 and 67 cents. Our standard deviation was 22 and 69 cents. If you don't put the rand symbol there, at all, it's not the end of the world. Bear in mind, we are talking about rands, so you should have the unit there, but it really is not the end of the world. Okay, so if you forgot, don't stress about it. Right, so 1.2.2 says, Mary also works part-time as a waitress at the same restaurant. Over the same 15-day period, Mary collected the same mean amount in tips as Reggie, but her standard deviation was 14. We'll get to all of that in a second. So we've got mean, we've got standard deviation, and we've got Mary and Reggie. Now you've just worked out Reggie's, so his mean was 94 and 67 cents, standard deviation 22.69. Mary's mean was exactly the same, but the standard deviation was slightly lower. Okay, so now that we have that summarized for ourselves, it says using the available information, comment on the total amount in tips that they each collected over the 15-day period. Now, we've only got mean and standard deviation to base some sort of answer off here. However, let's think about what this means. If the mean amount was the same, okay, so we're looking at the situation over here. Their mean amounts are the same, which means that if we think about what the mean is, the sum of all your values divided by the same 15 days, those sums would have to be equal for Mary and Reggie to get the same average. If we are dividing by the same 15 days, it means that the sum has to be the same. So when we talk about the total amount of tips, sum of, that they each collected, it was the same. Okay? Okay, that was trying to say same, but it didn't really work. Let's try that again. All right. So the same total because the averages or the mean was the same. So go back to basics, go back to how do we actually calculate these things? What does it mean in the greater picture, greater scheme of things? Right, question B though says comment on the variation that each of them received in daily tips over this period. So this is now when we need to compare the standard deviation. So Mary's standard deviation was 14. Reggie's standard deviation was the 22.69. Reggie's was greater, which means that he had a greater spread or greater variation in the amount of tips he got. So Reggie's is greater, or Reggie's, I'm going to be lazy, SD, standard deviation, is greater. Therefore, he had a greater variation in tips. Variation, greater difference. You could say difference if you wanted it as well. Okay, so understanding what mean and standard deviation actually do, it's very important. So that's why I asked you right at the beginning of this lesson, what actually is standard deviation? Because if we don't know what it means, it's not possible for us to answer this question. Ooh, golly, Miss Molly. Alrighty, I can't actually remember what we haven't screenshotted. So let's do this. Because I don't think we've done this. And I need to take that. I'm gonna fix myself right now. Okay. Oh my gosh. There we go. There we go. Right, now we have everything that we need. So let's take a screenshot there. I don't know if we'll get through all of the next question, but let's see how far we get. Right, so this was a grade 11 type question. Then we move into a grade 12 type question. As you go through past papers, you're going to see that this is stock standard for what's going to happen here in your paper. Right, so question 2. A familiar question among professional tennis players is whether the speed of a tennis serve in kilometers per hour depends on the height of a player in meters. The heights of 21 tennis players and the average speed of their serves were recorded during the tournament. The data is represented in the scatter plot below, and the least squares regression line is also drawn. Right, do you see that in this least squares regression line, it hasn't actually been extended past the domain? So that's what I was saying earlier. Don't extend it further than the data points that you have. So the first question says, write down the fastest average serve speed in kilometers per hour achieved in this tournament. So have a look and tell me what you think the fastest average serve speed was. Anyone? Bongi and Corsi, very nice. Do you want to explain how you got that that speed? No, okay, no problem. So fastest, look at the highest point in terms of your average speed, which is your y-axis. It's this point up here. Read across what value it is, 251. Okay, very straightforward. Don't have to stress too much about that. Right, so 2.2 says, consider the following correlation coefficients. We've got R equals 0.93, R equals negative 0.42, and R equals 0.52. Which one of the given correlation coefficients best fits the plotted data? So in the chat, give me A, B, or C. Which one do you think best fits the data set here? A, B, or C? Okay, Leila's giving me an answer. Can you say why you say that, Leila?
Oh, ma'am, I don't really know how to explain it, but it looks similar to the on the sheet that you gave. It looks similar to the line, the moderate positive linear correlation thing, where it's 0,
Lovely.
0.5 is like R is greater than that but less than 0.8. So it looks a lot similar and
Okay.
it matches the direction of the line. So that's why I picked that one.
Okay, if you look at, I'm so glad you said you have the sheet because I was definitely dreaming whether or not I did it. So thank you for putting my mind at rest. If you look at that and you compare it to the strong positive correlation, what is the difference in the spacing of the dots?
The dots in this one are more further spread apart than compared to the strong one.
Exactly. So guys, we are going to go with C because, as Layla said, firstly, it's definitely positive. This line is increasing from left to right. So we can immediately ignore B because that's not possible. It has to be positive. So we are considering A or C. And as Layla's just said, a correlation coefficient of 0.93, that is a strong positive correlation. The dots would be a lot closer to my least squares regression line. Whereas here, my dots are more spread out. They're further away from the least squares regression line. And so this is why we go with option C. Okay, so I appreciate you putting my mind at ease. We did speak about this. I will find the sheet again. I appreciate you actually having that. Sometimes I think I do things and no one actually cares, but thank you. I appreciate it. So we're going to go R is equal to 0.52, option C. And our reason for that, even though it doesn't ask us for a reason, we're going to give one anyway so that we know for ourselves. Because it's positive. Okay, we're just going to go with this, positive. And
Ma'am, they
my
actually asked the reason in the next question. Sorry.
oh, look at that. No, that's fine. I was thinking about this. I was like, I'm so sure I wrote down a reason. Okay, that makes more sense. Use the scatter plot and the least squares regression line to motivate your answer in question 2.2.1. Look at that. It's amazing what happens when we read. Right, so yes, exactly. The points are fairly scattered. That's an S, shame. Scattered. Whatever. Hence a lower R value, and the trend is positive. So it's going up from left to right. And so that's why we went with a positive moderate correlation coefficient value. Okay. Now it's only 1 mark, which means you don't need to give a whole essay, but you do need to reason it, and it's exactly what we've just said. Okay. Last one. I'm going to do the last two, but it's 1 mark each, so we're going to do it. What does the data suggest about the speed of a tennis serve and the height of a tennis player? Now, if you were to look at the memo, there are actually quite a few options. But if we think about what our correlation coefficient that we've chosen means, so I think Leila actually gave us a whole description. This is a moderate. Is it? It's a weak. A weak positive correlation. Layla, you can correct me because you have that information in front of you if I'm wrong. Okay, so it's a weak positive correlation, which is, thank you, which means that there is a correlation, but like it's not super strong. So what we're saying here is that height could have an influence, on serve speed. But it is not a strong relationship. It is not. Okay. So just bear in mind what those correlations mean. I will find this sheet and put it up again because... Right, and then the last one says the equation of the least squares regression line is given as y is equal to 27,07 plus b of x. Explain why in this context the least squares regression line cannot intersect the y-axis at 0,27,07. So quickly, obviously y equals mx plus c. C is your y-intercept, so your constant is your y-intercept. Let's think about what that means. If we had a y-intercept here, okay, it doesn't go all the way down there, so let's just pretend. Y-intercept at 0. Sometimes I do stupid things. And it's okay. It's okay to do stupid things, but sometimes really I need to be better. Right, so there's my point, 0, 27,07. X would be the height of our tennis player as it was on the scatter plot, and Y would be the speed. So given the fact that I've just said X is height, can you be 0 meters tall? Is that possible? And then still serve a serve with a speed of 27.07 kilometers? No, it's not possible. Okay, so that's why it says in this context, explain why I cannot intersect there. So it's not possible. That was a very aggressive not. I apologize. Right, so for you to be less than a meter, you're a child, you're an infant. And so we're talking obviously about professional tennis players, if I remember the professional tennis player. Now again, I'm not saying you can't be a professional tennis player at a small wee age. However, it's very, very, very unlikely. And so 0 meters, not possible. Okay, so just think logically. We're not trying to trick you out. Think logically about the question.